Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to lecture 6 of the course of CS352 Introduction to Soft Computing. This lecture is all about adversarial search techniques, a specific type of techniques in AI where two or more players are competing against each other. Let me reiterate the language that I'll be using during the lecture. During the whole of lecture 6, search techniques and in particular the adversarial search techniques, I'll be using English with sporadic use of Urdu here and there. At the end of the lecture, I'll be giving a summary in English, which will then be followed by a keynote or key points in the lecture that will be in Urdu. So for those of you who want to understand this in Urdu, I really recommend that you listen to the lecture first, try and understand it, and then after that you can move to the end of the lecture where all the key points are going to be present in Urdu for you guys to understand it easily. So let us start with looking at the contents of lecture 6, adversarial search, which is part of the course CS352 Introduction to Soft Computing. First of all, in section 1, we'll be looking at the topic searching in games, which is basically about introduction and background to games and how we look at games from the perspective of AI. Then we'll look at a specific algorithm called Minimax Algorithm, which is used to find the optimum value when two players are playing a game. Then in section 6.3, we'll talk about alpha beta pruning, which is a specific technique to improve the complexity of Minimax algorithm and is used in conjunction with Minimax algorithm. Finally, in section 6.4, we'll look at a very interesting topic, which is the current state of games when a man plays versus a machine. So here in this section, we'll basically be looking at how machines have improved or evolved over time and how they are now leading man in terms of at least gameplay. And we'll also see different techniques that have been applied in machine learning and in AI for this purpose. In the previous section, we had discussed the basic background that is necessary for you to understand adversarial search algorithms. In this lecture, we'll take a step forward and use the concepts that we have learned in the previous lecture. So just a quick recap for you. In the previous lecture, we had talked about what a game is. Then we had talked about how to formulate a game in terms of AI. And then we had discussed what a game tree is. And on that note, we had ended the previous lecture. So once you have the game tree defined, which algorithm will you apply to search the game tree and basically come up with the most plausible result? The algorithm that is applied for this purpose is called the Minimax algorithm, based on the names of the min and the max, and it basically calculates the most optimal value one can expect to get from a particular position at the end of the game. So it's again a planning phase where you will kind of automatically understand what to expect before actually playing the game, and we'll come to it in this section in the next slides. So let us start with looking at an actual algorithm that is used to find the maximum utility of a given position in a given game. In that regard, we'll first start with what an optimal strategy for determining game tree values would be, and how on a gene tree what result do we expect for a particular at the root node for a particular position. Then we'll discuss an algorithm called Minimax algorithm that is used to evaluate the maximal utility on a given gene tree. Then we'll actually apply it on a particular case of a game tree and see how the results are. After discussing Minimax algorithm, we'll then discuss the properties of Minimax algorithm. And then just for a quick overview, I'll talk about the time complexity of actual games. And it is in relation to this particular part, the time complexity of actual games, that we can discuss the limitations of Minimax algorithm. So before starting with Minimax algorithm, let us think about what an optimal strategy should be and how it should look like. The idea here is that since it is the max turn to start the or select the highest value at the root, so max must find a contingent strategy which can specify the max move in terms of the initial state that is going to be the starting point and the states that are resulting from for every possible response by min. So in this particular example, we see a two-ply game where the tree is one move deep, consisting of two half moves. We call them half move because they are moves by each individual player, one move by max and one by min, and each of these half moves is called a ply in terms of the game tree. So this is a two-ply game, and in this particular game, max, for example, has already chosen the values 3, 12, 8, 2, 4, 6 and 14, 5 and 2, and then min is supposed to choose the lowest value out of 3, 12 and 8, and of course the lowest value here is 3. Then it chooses 2 from the pool of 2, 4 and 6 as shown here, and then it again chooses 2 from the pool of 14, 5 and 2. Now max is going to make the next move, and he has the choice of choosing either 3, 2 or 2, and of course he has to, since he's maximizing, he will choose 3 out of this. This completes the basic game tree, and now we want to determine an optimal strategy for this, and this is where the Minimax algorithm comes into play. So what is the Minimax algorithm in AI? The Minimax algorithm is a recursive or backtracking algorithm which is used in decision making and game theory. It provides an optimal move for the player, assuming that the opponent is also going to play optimally. The Minimax algorithm uses recursion to search through the game tree. The Minimax algorithm is mostly used for game playing in AI, typically games such as chess, checkers, tic-tac-toe, Go, and various other two-player games. This algorithm computes the minimax decision for the current state and then pushes it up the tree. In this algorithm, two players play the game. One is called max and the other is called min. Both the players fight it as the opponent player gets the minimum benefit while they get the maximum benefit for self. Both players of the game are opponents of each other, where max will select the maximized value and min will select the minimized value. The Minimax algorithm performs a depth-first search algorithm for the exploration of the complete game tree. Please note that the breadth-first search cannot be performed for the Minimax algorithm, since the breadth-first search would basically explore the alternate node on the same level, and the same level indicates the same player making another choice. But that is not true, because to choose the minimum or the maximum of the given choices, one must choose from the values given by the opponent. The Minimax algorithm proceeds all the way down to the terminal node of the tree and then backtracks the tree as the recursion. The pseudocode for Minimax algorithm is given here, but for the sake of our audience, which is basically Pakistani and Urdu speaking, I'm going to explain it in Urdu. Here is a pseudocode for Minimax algorithm, and I'll try to explain it in Urdu for you guys so that you can grasp it better. आइडिया बहुत सिंपल है. आइडिया स्टार्ट हो रहा है, सबसे पहले आप एक ही फंक्शन है जो कि दोनों मिन भी और मैक्स भी इसी को कॉल करेंगे और इसी कोड को यूज़ करेंगे. सो जो इनिशियल कॉल है वो मिनी मैक्स जो फंक्शन का नाम है, उसको आप बेसिकली रूट नोड या वो नोड जहाँ पे है वो पास करते हैं, किस डेप्थ पे है वो पास करते हैं, और उसके साथ बताते हैं कि ये किसके लिए यूज़ हो रहा है। अगर मैक्स के लिए यूज़ हो रहा है तो ये ट्रू है, अगर मिन के लिए यूज़ हो रहा है तो यहाँ पे ये फॉल्स है। अच्छा, इनिशियल कॉल ये हो गई। इनिशियल कॉल के बाद फंक्शन के ऊपर आते हैं। सो फंक्शन में नोड है, किस डेप्थ पे परफॉर्म हो रहा है और किस प्लेयर के लिए परफॉर्म हो रहा है ये बताना है। और अगर तो डेप्थ आपकी ज़ीरो है या फिर नोड जो है वो टर्मिनल नोड है, ठीक है, तो उस केस में जो भी आपकी इवोल्यूशन है वो आपने सिंपली रिटर्न कर देनी है, ठीक है। अच्छा, अगर ये टर्मिनल नोड नहीं है और डेप्थ जो है वो ज़ीरो के अलावा कोई और वैल्यू है, तो इन डैट केस आप चेक करेंगे किस प्लेयर के लिए है ये, ठीक है। तो अगर तो ये मैक्सिमल प्लेयर के लिए है तो फिर आपने क्या करना है, मैक्सिमाइज़र के लिए आपने मैक्सिमम इवैल्यूएशन को -∞ से स्टार्ट करना है, और उसके हर चाइल्ड के लिए आपने क्या करना है कि आपने मिनी मैक्स को एक डेप्थ कम करके और दूसरे प्लेयर के साथ, यानी ये क्योंकि मैक्सिमाइजिंग प्लेयर के साथ था, मैक्सिमाइजिंग प्लेयर वाज बेसिकली द मैक्स, इसका मतलब है कि दोबारा आपने एक डेप्थ कम करनी है और ये आपने मिन से पूछना है कि वो अपने रिजल्ट्स दे हर चाइल्ड के लिए, जो रिज़ल्ट आएगा हर चाइल्ड के लिए उसमें से आपने मैक्सिमम को सिलेक्ट करना है, ठीक है, और मैक्सिमम को सिलेक्ट कर बेसिकली आपने वो वैल्यू रिटर्न कर देनी है। अच्छा, ऑन द अदर हैंड अगर ये मिनिमाइज़र के लिए आप कर रहे हैं तो देन आपने पॉजिटिव इन्फिनिटी से स्टार्ट करना है, यानी कि सबसे बड़ी वैल्यू, और उसको कम से कम करते जाना, जो उससे छोटी वैल्यू मिलती जाए उसको सिलेक्ट करते जाएं, ठीक है। और सेम प्रोसीजर गोज़ के पहले तमाम चाइल्ड के साथ पूछें और वो हर चाइल्ड जो है वो मैक्सिमम या मैक्सिमाइज़र का रिजल्ट आपको दे रहा हो। तो इसलिए आप यहाँ पे ट्रू देख सकते हैं, एवा इज इक्वल टू मिनी मैक्स चाइल्ड डेप्थ -1 कॉमा ट्रू। ट्रू मीन्स कि ये मैक्स से पूछ रहा है, और उसके बाद वो मिनिमल वैल्यू सेलेक्ट करेगा, उसको रिटर्न करता जाएगा। The working of the Minimax algorithm can be easily described using the following example. Below, we have taken an example of a game tree which is representing the two-player game. In this example, there are two players. One is called maximizer and the other is called minimizer. The maximizer will try to get the maximum possible score and minimizer will try to get the minimal possible score. This algorithm applies depth first search, so in this game tree, we have to go all the way through the leaves to reach the terminal nodes. At the terminal node, the terminal values are given, so we will compare those values and backtrack the tree until the initial state occurs. Following are the main steps involved in solving the two-player game tree. In the first step, the algorithm generates the entire game tree and applies the utility function to get the utility values for the terminal states. In the tree diagram, you can see, let's take A as the initial state of the tree. Suppose maximizer takes the first turn, which has worst case initial value -∞, and minimizer will take next turn, which has worst case initial values +∞. So since the game tree is now initialized, we will then go on to step 2, where we first find the utility values for the maximizer, initialize all the values with -∞, so that we can compare each value in terminal state with the initial value of the maximizer and determine the higher node's value. So it will actually find the maximum among all the values. So for node D, the first thing is to find the maximum between the value of H and the value of D, which is -∞. So the value is, of course, the higher value is -1. The second step, we find the maximum value between -1 and 4, which is the value of node I, as you can see in the figure. And the higher value between -1 and 4 is 4, so maximizer will choose the value 4 for node D. Similarly for node E, first we'll compare the value of node J with -∞, and then whichever is higher will basically compare that value with the value of node k, which is 6. So 2 and minus infinity, when you compare them, the value is 2. Then we should compare 2 and 6, and the higher value is 6. So the answer for node E is 6. Similarly for node F, if you compare minus infinity and minus 3, the answer is minus 3. Then you compare minus 3 with the value of node M, which is minus 5, minus 3 and minus 5, the higher value is minus 3, you select minus 3. Okay, similarly for node G, we compare basically minus infinity with 0, the answer is 0 as the higher value, and then we compare 0 with 7, and the higher value is 7. So for node G, the answer is 7. In the next step, it's the turn of minimizer. So now it will compare all node values with plus infinity, and then we'll find the value for the third layer nodes. So we'll basically, the minimizer is supposed to find the value for node B and C. For node B, what he has to do is he has to take the minimum value between minus infinity and the value of D, which is plus 4, and the value of node E, which is plus 6. So plus infinity, 4 and 6, the lowest value, since it is minimizer, it will have to find the minimal value. The minimal value between them is 4, so the value of node B is 4. Similarly for node C, it will compare plus infinity with the selected value for F and G by maximizer, which is minus 3 and 7. And out of these three, the minimal value is minus 3. And that's about it for minimizer. Continuing the recursive step, it is now the turn of maximizer, and it will again choose the maximum of all nodes values as it did in the 2 steps back, and find the maximum value for the root node. So in this game tree, there are only 4 layers, hence we reach immediately to the root node. But in real life and real games, there will always be more than 4 layers, as you can see probably in the next slides when I'll be talking about the current state and the challenges that are faced in real games. But for now, the value for node A that will be chosen by the maximizer would be the maximum of the value of node B and C, the children of A. The value of node B is 4, the value of node C is minus 3. That was chosen by minimizer, and since maximizer has to choose the maximum of these two, the maximum of these two, 4 and minus 3 is basically 4. So the value for node A is 4. And with that, we have basically completed the Minimax algorithm, since we have found the value of chosen by the maximizer at node A. What you need to keep in mind is that after running this algorithm, we are kind of sure that if everyone plays optimally, if you and your opponent, the maximizer and the minimizer, both of them have played optimally, then the best deal that we can get out of this whole system is plus 4. But what happens, you need to think about this point, that what would happen if the game was not played optimally by your opponent. So for example, the minimizer chooses a wrong value. Well, the thing that would happen is you will get a larger value than expected. You are expecting the best that you can expect from this particular game, from this particular scenario, is that you can maybe get 4, right? If everyone plays optimally. But if they don't play optimally, if your opponent does not play optimally at least, then you can expect to increase your output. Your output could be greater than 4. It could be 7, it could be 6, it could be some other value that was chosen incorrectly by your opponent, the minimizer. So in short, Minimax algorithm actually gives you the worst case scenario, that is that even if your opponent plays perfectly fine, perfectly optimal, then the maximum that you can get out of this particular scenario is this particular score, whatever it is. In a tic-tac-toe game, for example, it could have been simply like you could win in any case, or you could lose from a particular case or whatever. But in the worst case scenario, you might not lose actually. So, like we have always done, whenever we have started an algorithm, we always talked about the 4 main properties of the algorithm. We'll discuss the same properties here again. First of all, what you need to do is whenever you see an algorithm, like I've always said, you need to talk about whether it is complete or not. Min-max algorithm is complete. It will definitely find a solution if it exists in the finite size tree. When then we can talk about optimality. Min-max algorithm will definitely be optimal, but the condition here is that if both opponents are playing optimally, both the players min and max should play optimally, and then this is going to give you an optimal solution. At least if you're trying to maximize the values of max, then we can always think of, even if minimizer is not playing optimally, still you'll probably get the most optimal result or better result than what's to be expected. Then regarding time complexity, you need to understand that since the Minimax algorithm is performing DFS, as I've already told before, for game tree, the time complexity of Minimax algorithm is the same as that of depth first search algorithm, which is big O of b to the power m, where b is the branching factor of the game tree and m is the maximum depth of the tree. Then if you talk about the same complexity, space complexity, it is the same as that of depth first search, which is basically big O of b multiplied by m. So in this example, you can see how we have applied Minimax to a small portion of a game of a tic-tac-toe. At the top, what you can see is it is max turn, and max has to choose one of the three configurations. The three configurations are again chosen from some further configurations by min in the next step, and at the bottom again it is a max turn to select some. What you can see is at the in the fourth row at the bottom, each of the four leaves have basically a utility value of +1 or 0. So max chooses some of these, and of course there are some additional moves as well, which are also leaves where you can see that min has already won the game and they are being assigned a utility value of -1. The utility value is defined by a blue color, while the ones that are being chosen by max are in black or color, which are chosen by either max or min. It's in black. So if you go back, because it's a backtracking algorithm, the first thing is that you're actually starting from max, but the final decision will be shifted down and down and down until you reach the leaf values, and from there you backtrack and assign values up the tree. And if you look at this, so for example at the bottom left, you can see an utility value of +1 because the max has won the game. If you backtrack it a bit, it's still +1, one step back. If you move 2 steps back, since it's min turn, min will always go for the place where the O wins. So it's going to have a utility value of -1. Similarly, -1 for the second one, and then finally for the third one, if it has a choice between a draw and a win for max, it will always choose a draw. And hence, if we go now to the root, max has 3 choices. In 2 out of them, max is going to lose, and in one he can draw the match. So he'll choose to draw the match. As you have seen that the Minimax algorithm is complete and is optimal as well, then why is game playing so hard? Like, why is still machines not able to win against humans, and why is the problem actually hard to tackle? The answer lies in the complexity of actual games. The example that we saw earlier, tic-tac-toe, is relatively a very small game, and as you can see, the complexity at best is maybe if you talk about the game tree complexity, it is 10 raised to power 5, which is almost 100,000 and not too difficult to exhaustively explore. But as we go on and increase the complexity to higher games, for example international draft or chess or backgammon or even Go for that matter, you can see that the game tree complexity rises exponentially. So for example, for draft, the game tree complexity is 10 raised to power 54. For chess, it is 10 raised to power 123. For backgammon, it is 10 raised to power 144. And for a typical game of Go, it is 10 raised to power 360. So if you compare these numbers with, for example, tic-tac-toe, you'll feel that the complexity is exponentially rising, and 10 raised to power 54 is even a number that is, I think, almost computationally infeasible for games to handle for determining each single move. And in this regard, therefore, the Minimax algorithm cannot be used for actual games, other than maybe tic-tac-toe at best. So far, we have seen two players who are playing the Minimax game, and the Minimax algorithm that we have seen so far actually compares and maximizes the utility for two players. But what happens when there are more than two players? Let us suppose that there are three players called A, B, and C, and they are competing on the same game. And in general as well, there are a lot of games that have more than two players. For example, Ludo, or for example, Carom, or other games where more than two players are playing. So in that case, can we apply Minimax algorithm? The answer to this question is yes, we can. We just need to extend the idea of Minimax to multiple players. So if you characterize Minimax as minimizing a single value, that is what we have seen so far, or maximizing a single value actually. But in this particular case, when there are more than two players who are competing, in that case, we can basically say that each player has his own utility that he wants to maximize. And this will not be a zero-sum game for sure, okay, but it will still be a game. And in this particular case, what we need to do is we just need to worry about our own utility. So for example, in this case, in the figure shown, what you can see is it is a turn of A and at the leaf, and he has basically selected 8 different nodes with the utilities that are given. So the first utility in the tuple is basically 1, which is of A. The second utility that is given in the tuple, which is 2, is of B. And third utility that is given, 6, is basically of C. And similarly, if we go to the second node from the bottom left, we see that A has a utility value of 4, B has a utility value of 2, and C has a utility value of 3. What you can notice is that each utility value is basically independent of the other utility value. It would not have been possible in the case of zero-sum games. So that is a difference that you need to keep in your mind. With that difference in mind, what we can say now is that we can simply extend the idea of Minimax at each level, where you just pick the one that maximizes your own utility, and let's forget about other utilities at the moment, although that may come into play during a game. So for example, let's take the simplest case. It is a turn of C to choose a value for a node. Let's take the leftmost node of C. The node of C is in yellow color, and what we see here is that C has to choose between 1 to 6 and 4 to 3. So all C needs to do is just look at the utility value of C, which is 6 in the first node and 3 in the second node. And since 6 is larger, C will always choose 1 to 6 as its option. Similarly, for the second yellow node, it has an option of choosing between 612 and 741. Since 2 is greater than 1, so it will always choose the first one again, so it will be 612 that gets chosen. Similarly, it chooses 152 and 545. Then it is a turn of B, which has a choice between 126 and 612. Again, it will just look at the second variable, which is basically 2 in the first node and 1 in the second node, and of them, of course, 2 is greater, so it will choose 126. Similarly, when it has to choose between two nodes 152 and 545, it will choose the one that is larger in the second variable, which is 5. So it will automatically choose 5 over 4, that is the first variable again, 152. Okay, then it is a turn of A, which basically has a choice between 126 and 152. In this particular case, if you can compare both, it's 126 is 1 is equal to 1, so it can choose either 126 or 152 depending on what it needs to what it selects. So in this case, it has selected the first one. It is a very interesting phenomena in this case that let's suppose that you're playing a game there are basically two or more players, and one of them is going very strong. So a lot of times you have been playing in Ludo where everyone is an individual player and he just wants to win, and at times there is a certain player who is going very strong, and you could actually form an unannounced, or let's say an unintended even alliance with one of your opponents, such that you are going to go against the strongest player. You basically want to beat the strongest one first, so that he does not win the game, and then you both could maybe share the or compete for the winning position after that. So what we see here is that in when you extend the idea of minimax onto multiple players, more and specifically more than two players, then it is not a zero-sum game. It is not a pure competition. It might form unannounced alliances, and you might basically be partnering with someone without even announcing it. You might be helping out some other person or player just because you want the stronger one to be beaten. So this becomes very interesting when the idea is extended onto multiple players, specifically more than two players. And we have seen a lot of common examples from the common life where actually the minimax algorithm needs to be extended onto multiple players. In particular, for example, many first shooting games and many other games where there is no team, or basically every player is playing for himself or herself. In that case, you will see a lot of times that the idea of minimax is actually extended onto multiple players. So since we are done with the major part of Minimax algorithm, we should discuss the limitations of Minimax algorithm as well. The main drawback of the Minimax algorithm, while as you can see it's already optimal and complete, I think the main issue is the same as that of depth first search. It's time complexity. The issue is that if you go for really complex games, for example chess or Go, etc., the time complexity of big O of b to the power m, which is an exponential complexity, gets really slow. And think about, it's not just one move that you're going to take. After each move you need to reassess and you need to come up with a better answer. So and you need a heuristic function that gives you the terminal values, which I'll discuss maybe at the end of this slide. But what you need to really remember is that for big games like Go and chess, which have a huge branching factor and which basically indicates that the player has lots and lots of choices to decide at each depth, the minimax algorithm is going to be really slow. And in this regard, I'll quote a computer scientist called Victor Ellis, who basically says that typical games of Go, the Chinese Go, between experts usually last about 150 moves, with an average of about 250 choices per move, suggesting that the game tree has a complexity of 10 to the power 360. This limitation of the minimax algorithm can be improved, of course, by using alpha beta pruning with minimax, which we are going to study in the next section. But we really need to keep this in mind that the algorithm or the adversarial search algorithm that was used, let's say 10 years ago or earlier, the minimax algorithm had a really bad time complexity, and that is where which was kind of the blocking factor or the stopping factor for AI not to grow further, and deep learning actually broke this particular barrier for AI. Before that, that was the ultimate limit, big of b to the power m, and we were going at an exponential level, and I think it was the exponential time complexity was killing the system. And the main usage of Minimax algorithm, I mean, if I have to come up with one question that you might have thought when I was teaching Minimax is, how did the values come for the game tree? So you see a game tree, and I told you that the values at the leaf roots, at the leaf states are given, right? So how did we get those values? The answer to that is that actually at the leaf we basically have a heuristic function or something that calculates a value for us. So let's say that we just want to go till depth 12 for a chess game, and there's a heuristic function that which intakes a state, and it gives you a heuristic value for it. For example, it can just sum up the value of different pieces on the chess game. The pawn maybe for 1 point, let's say the horse for 2 points, the bishop for 3 points, the castle for 4 points, and maybe so on and so forth. And it might give you some points for it. That is one simple way, and it can evaluate it for you, each situation, and then it can just give those as you go down till depth 12, generating all the possibilities, and at that particular point, depth 10 or whatever depth you want to go, depth 8 or and at that particular depth, what we're trying to do is we then apply this heuristic function, which gives us a value for each state. That's it, and that value we'll just feed in our game tree, and then we'll grow up from bottom to top, assuming that each alternate layer we get a turn, and on the other layer the opponent gets a turn. So it is a very important question that what do the terminal values represent and how they are achieved for this particular tree. Other than that, I think everything else in Minimax is really simple. All you need to worry about is how did the time complexity come. You need to know the derivation of it. It's very simple, but you need to know how to derive it, and it's something that's related to depth first search, and you need to go and look at that particular algorithm when I was teaching it. बाकी मैं यही कहूँगा कि ये बहुत आसान है, आपको इसमें ज़्यादा घबराने की ज़रूरत नहीं है. मिनीमैक्स का स्टैंडर्ड मेथड आपको आना चाहिए. इसके कुछ कॉन्सेप्चुअल क्वेश्चंस हैं जो मैं आपको साथ साथ बताता गया हूँ, ठीक है. वो हो सकता है लिखे हुए ना हो, बट आपको जो है वो लेक्चर में अगर आप ऑडियो सुने तो उसमें मिल जाएंगे, एंड दिस विल हेल्प यू प्रिपेयर फॉर द फाइनल एग्जाम एज वेल. तो इस लेक्चर को गौर से सुने, इसकी एक एक बात को ध्यान से सुन के बेशक साथ नोट करते जाएं. एट टाइम्स इट माइट नॉट बी इनफ फॉर यू टू जस्ट सी द स्लाइड्स. बाकी इट्स रियली सिंपल. इट इज़ समथिंग दैट you can easily just go through the lectures and learn. और इसके बाद मैं कुछ एडिशनल रीडिंग्स की भी स्लाइड्स आपको यहाँ पे दे रहा हूँ, which might give you some additional examples. जो अगली स्लाइड है उसमें एडिशनल रीडिंग के नाम पे मैंने कुछ वीडियो ट्यूटोरियल्स डाले हुए हैं, उनको देखकर भी आपको मज़ीद कुछ बात समझ आ जाएगी. डू गो एंड वॉच द यूट्यूब वीडियोज़ जो मैं नेक्स्ट स्लाइड में डाल रहा हूँ. बाकी बेस्ट ऑफ लक. Let us now quickly summarize section 6.2. Max must find a contingent strategy to know what it can expect at best to gain from a given position of a game without actually playing the game, and there's also a hidden assumption here that the opponent will play optimally and not make a mistake. So in this particular scenario, Max will try to find the best he can gain out of this particular situation. Then Minimax algorithm is typically used in many games in AI. So a lot of searching games that you see and where a computer is playing against you, it will basically be employing Minimax algorithm underneath. What do we mean by optimal move? An optimal move depends on the player which is trying to play it. An optimal move for the maximizer is basically going to find the maximum possible score from all the possible options that are in a game tree. If I'm talking about a game tree, then it's basically the children. From the children, you choose the maximum possible answer. That's the optimal move for the maximizer. On the other hand, the optimal move for minimizer will be the minimum possible score of all the possible children in the tree under the given node. Then Minimax algorithm is complete, optimal. It has a time complexity of big O of b to the power m, that is, it is exponential, where b is the branching factor and m is the basically the depth of search, and that space complexity is big O of b multiplied by m. So if you take the time complexity and space complexity, that is precisely the same as the depth first search algorithm. So most games are extremely complex and require extensive searching, which makes Minimax algorithm extremely inefficient. And basically, in terms of calculation, you have to use heuristics to cut off the tree at a particular depth or a depth limited search somehow, because the exponential time complexity makes it almost impossible to go beyond 8 or 10 depth in a reasonable space in a reasonable time. And another issue I think would be that in most games you actually want the player to have time constraints as well. And in that case, for example, let's say chess, you have a time constraint of 15 minutes per game or something like that. So it more or less a computer is supposed to make a decision in a relatively quick time, and if you have to perform such a big search, it would take it a lot more time to search the solution, and then it becomes impossible to use it for the given game. Then Minimax is hence not very useful with games with very large branching factors and complexity. For example, the game of Go and the game of chess. Minimax algorithm is not very useful directly, although people still use it, but then they need to have very smart heuristics to kind of estimate the goodness of a position. And maybe you just need to search maybe 12 plies or something, and then you need to come up with a possible heuristic value or a functional value or a fitness value, if you want to call it. Then we saw that Minimax algorithm can be extended to be used for 3 or more players as well. But there's just this point that you need to realize that however, the game will then not be a zero-sum game. So then there has to be some kind of alliances or maybe favors that might need to be done at certain points. So with that, I think we are done with the section 6.2. I'll now translate all of this, the summary and the key points into Urdu for my audience, which is basically the students of CS352. अब हम इस सेक्शन के अहम नुकात का बगौर मुतालिया करेंगे और देखेंगे कि इस सेक्शन में हमने क्या सीखा. सबसे पहले तो ये है कि जो हमने पहले देखा गेम ट्री देखा और गेम ट्री में हमने वैल्यूज़ देखी, उन वैल्यूज़ को फिल इन करने के लिए हम मैक्स और मिन दोनों के पास है, जो भी प्लेयर है जो इसको इवेल्युएट करना चाह रहा है, जो इस पोजीशन को चेक करना चाह रहा है, उसके पास एक ना कोई स्ट्रेटजी होनी चाहिए, कोई ना कोई एल्गोरिथम होना चाहिए, कोई ना कोई तरीका होना चाहिए, ताकि वो खेलने से पहले ही उसको मालूम हो कि वो एक जिस भी पोजीशन में है करंटली, ठीक है, उससे वो सबसे ज़्यादा अगर दूसरा प्लेयर भी जो है वो बिल्कुल ज़बरदस्त खेले, परफेक्ट खेले, ठीक है, कोई गलती ना करे, तो वो इस सूरत हाल में वो क्या रिज़ल्ट एक्सपेक्ट कर सकता है, ठीक है. यानी अगर वो ख़ुद भी कोई गलती ना करे और दुश्मन भी कोई गलती ना करे, जो ओपोनेंट है वो भी कोई गलती ना करे, तो वो कितना अच्छा रिजल्ट ला सकता है, ठीक है. और ये काम ज़ाहिर है खेलने से पहले वो कर रहा है, तो दिस इज़ इन द प्लानिंग फेज़. बाद में खेलेगा, उसको मालूम पहले से होगा कि वो क्या मैक्सिमम क्या एक्सपेक्ट कर सकता है, और उसमें अगर ओपोनेंट गलती कर जाता है तो ऑफ कोर्स उसका रिजल्ट उससे बेहतर ही आएगा. और ये बात आपको अच्छी तरह समझ होनी चाहिए कि अगर ओपोनेंट गलती करेगा तो वो रिज़ल्ट उसका उससे जो एक्सपेक्टेड रिजल्ट है उससे ज़्यादा बेहतर हो जाएगा. अच्छा, फिर हम बात करते हैं कि मिनीमैक्स एल्गोरिथम जो है वो एक एल्गोरिथम है जो कि एक्चुअली एक जो मैंने आपको इससे पहले जिक्र किया कि एक स्ट्रेटजी है। स्ट्रेटजी का नाम है मिनीमैक्स एल्गोरिथम, जो कि आम तौर पे बहुत ज़्यादा गेम्स में एआई में इस्तेमाल हो रही हैं। अच्छा, इससे पहले हमने जिक्र किया था कि ऑप्टिमल मूव, यानी कि ओपोनेंट गलती नहीं कर रहा, ऑप्टिमली खेल रहा है। तो ऑप्टिमल मूव का मतलब क्या? ऑप्टिमल मूव का मतलब ये है कि बेसिकली डिपेंडिंग ऑन द प्लेयर, ठीक है, इसके मतलब मुख्तलिफ हो सकते हैं। मसला अगर मैक्सिमाइज़र के सेंस में सोचा जाए तो मैक्सिमाइज़र की नज़र में ऑप्टिमल मूव वो होगी जो कि उसके तमाम पॉसिबल मूव्स में से, तमाम चांसेस में से वो वाली मूव ले जिससे कि उसको सबसे ज़्यादा स्कोर मिले, ठीक है। जबकि अगर मिनिमाइज़र के नुक्ता निगाह से देखा जाए तो उसमें मिनिमाइज़र हमेशा उस तरफ जाने को प्रेफर करेगा जिसमें कि स्कोर मिनिमल हो। यानी कि बेसिकली अगर हम एक नोड पे हैं और उस नोड पे हमने चूज़ करना है फ्रॉम द चिल्ड्रन, तो ऑप्टिमल मूव डिपेंड करेगी कि चूज़ कौन कर रहा है। अगर मैक्सिमाइज़र को चूज़ करने दिया जाए तो वो उन चिल्ड्रन में से उस चाइल्ड को चूज़ करेगा, उस पाथ को चूज़ करेगा जिससे कि स्कोर मैक्सिमल हो रहा होता है। जबकि अगर मिनिमाइज़र को चूज़ करने दिया जाए तो मिनिमाइज़र उनमें सबसे कम स्कोर वाले चाइल्ड को चूज़ करेगा और उस पाथ को लेगा। अच्छा, अगर हम मिनीमैक्स एल्गोरिथम की प्रॉपर्टीज़ की बात करें तो मिनीमैक्स एल्गोरिथम जो है वो कंप्लीट है। यानी कि बेसिकली अगर सोल्यूशन एग्जिस्ट करता है, मिनीमैक्स एल्गोरिथम गारंटी करता है कि वो सोल्यूशन ढूंढ कर देगा। मिनीमैक्स एल्गोरिथम जो है वो ऑप्टिमल है। ऑप्टिमल का मतलब यहाँ पे ये है कि अगर एक से ज़्यादा सोल्यूशन एग्जिस्ट करते हैं तो आपको सबसे करीब वाला सबसे बेहतरीन सोल्यूशन वो ढूंढ के देगा। अलबत्ता इसकी खूबियाँ हैं, कंप्लीटनेस है, ऑप्टिमल है, ऑफ कोर्स की खूबियाँ हैं, लेकिन फिर इसकी बुराइयाँ हैं। बुराइयाँ इसकी ये हैं कि इसकी जो टाइम कॉम्प्लेक्सिटी है वो एक्सपोनेंशियल है, बिग O ऑफ B टू द पावर m है, और जो स्पेस कॉम्प्लेक्सिटी है वो बिग O ऑफ B मल्टीप्लाइड बाय m है। और अगर आपको याद हो तो ये दोनों जो बल्कि चारों प्रॉपर्टीज़ जो हैं, चारों तो नहीं कह रही, जो टाइम कॉम्प्लेक्सिटी और स्पेस कॉम्प्लेक्सिटी की प्रॉब्लम है, इनकी जो ये प्रॉपर्टीज़ हैं ये बिल्कुल वही हैं जो कि डेप्थ फर्स्ट सर्च एल्गोरिथम की भी थी। अच्छा, फिर हम बात करते हैं कि मोस्ट गेम्स आर अब अगर हम गेम्स की बात करें तो गेम्स की टाइम कॉम्प्लेक्सिटी हमने देखी थोड़ी सी। और टाइम कॉम्प्लेक्सिटी का मसला ये है कि नंबर ऑफ़ स्टेप्स को अगर देखा जाए गेम्स के तो ज़्यादातर गेम्स जो हैं वो बहुत ज़्यादा कॉम्प्लेक्स हैं। उनकी जो है 10⁻50, 10⁻100 और इससे भी ज़्यादा जो है उसके नंबर ऑफ़ नोड्स हैं जो इनको एक्सप्लोर करना पड़ता है। और इसके मतलब ये है कि हमें जो है वो इंतहा दर्जे की ज़्यादा आपको सर्चिंग परफॉर्म करनी पड़ेगी। और क्योंकि ऑलरेडी हमने देखा कि जो हमारा मिनीमैक्स एल्गोरिथम है उसकी कॉम्प्लेक्सिटी एक्सपोनेंशियल है, तो इसका मतलब ये है कि मिनमैक्स एल्गोरिथम जो है वो ज़्यादातर केसेस में इस्तेमाल नहीं हो सकता या बहुत इनएफिशिएंट होगा। तो तरीक़ाकार उसका ये होता है कि आप डेप्थ लिमिटेड सर्च करते हैं और डेप्थ लिमिटेड सर्च के साथ एक ख़ास डेप्थ नॉर्मली 10, 8 या 12 मैक्सिमम की जा सकती है इस डेप्थ तक। उस डेप्थ में आप जो हैं वो जाते हैं और उस जगह पे जाके देयर इज़ अ हेरिस्टिक टू काइंड ऑफ अप्रॉक्सीमेट द गुडनेस, यानी कि आपने एक हेरिस्टिक का इस्तेमाल करना है जो कि आपको उस लीफ नोड की जो 12वें डेप्थ पे हैं उसको लीफ बना देगा और उस पर एक आपको एक वैल्यू दे देगा जो कि उस स्टेट की गुडनेस बता रही होगी, ठीक है। अच्छा, फिर इसके बाद जो मिनीमैक्स एल्गोरिथम है इसी लिमिटेशन की वजह से, इसी कॉम्प्लेक्सिटी की वजह से, उस ख़ास तौर पे इसका हेरिस्टिक डिफ़ाइन करना या फिटनेस फंक्शन डिफ़ाइन करना जो है वो बड़ा मुश्किल काम है। तो आम तौर पे गेम्स में बहुत ज़्यादा हद तक इस्तेमाल नहीं हो सकता, ख़ास तौर पे वो वाली गेम्स में जिनमें बहुत ज़्यादा बड़ा ब्रांचिंग फैक्टर हो और उसकी कॉम्प्लेक्सिटी भी बहुत ज़्यादा हो। मसलन गो और चेस की इस तरह हमने बात की, उसकी कॉम्प्लेक्सिटी बहुत ज़्यादा है, तो उन गेम्स में मिनीमैक्स एल्गोरिथम का इस्तेमाल होना मुश्किल है। अच्छा, फिर हमने एक और चीज़ देखी कि मिनीमैक्स एल्गोरिथम जो है वो एक्सटेंड किया जा सकता है। अगर हमने तो 2 प्लेयर्स के लिए देखा इसमें और उसकी एग्जांपल देखी, लेकिन इसको बआसानी हम 2 से ज़्यादा प्लेयर्स के लिए भी इस्तेमाल कर सकते हैं, तो 3 या 3 से ज़्यादा के लिए भी किया जाएगा। अलबत्ता ये बात याद रखने वाली है कि जब 2 प्लेयर्स थे तो ये ज़ीरो सम गेम थी, यानी एक की जीत दूसरे की हार थी, दूसरे की जीत पहले की हार थी। एक का नफ़ा दूसरे का नुकसान, दूसरे का नफ़ा पहले का नुकसान। लेकिन मसला ये है कि जब 3 या 3 से ज़्यादा प्लेयर हो जाएंगे तो ऑटोमेटिकली उसमें नफ़ा नुकसान नहीं होगा, उसमें सिर्फ अपना अपना नफ़ा देखना है। तो इट विल नॉट बी अ ज़ीरो सम गेम, जो कि हमने इससे पहले देखा था, ज़ीरो सम गेम का जिक्र किया था, तो ये ज़ीरो सम गेम नहीं होगी। यानी कि मुमकिन है कि एक से ज़्यादा प्लेयर्स जो हैं वो आपस में मिल के अलायंसेस बना लें फॉर लेट्स से अगेंस्ट अ वेरी स्ट्रॉन्ग पर्सन, दूसरा एक तीसरा ओपोनेंट है जो बहुत स्ट्रॉन्ग है, उसके अगेंस्ट बाकी दोनों मिल के जम के खेलें, ठीक है। तो इसमें ज़ीरो सम नहीं होगा, दूसरे को नुकसान नहीं पहुंचाएंगे, वो गालिबन पहले को नुकसान पहुंचाने की कोशिश करेंगे। इसके साथ ही ये सेक्शन जो है वो अख्ताम पजीर हुआ। मैं उम्मीद करता हूँ कि आपको ये सारी बातें समझ आई होंगी। अगेन शुरू में हमने सारा कुछ इंग्लिश में रखा है, लेकिन आखिर में मैंने आपको समरी या की पॉइंट्स जो हैं वो उर्दू में बता दिए हैं। इसी तरह जो बीच में एल्गोरिथम एक्सप्लेन किया हुआ है वो उर्दू में किया हुआ है, लेकिन मैं एक्सपेक्ट ये करता हूँ कि आप एग्ज़ाम में इंग्लिश में ही लिखेंगे और आपको ये सारी बातें समझ आई हैं। इसके अलावा मैंने रिकमेंडेड रीडिंग्स दी हुई हैं जो कि लेक्चर वीडियो में भी हैं, और आई विल आल्सो पुट देम इन द बायो ऑफ द अपलोडेड वीडियो, ठीक है, ताकि आप लोग उसको आराम से देख सकें। ज़रूर जाके देखिएगा, उसको पढ़ने की कोशिश करिएगा, उससे आपके इल्म में मज़ीद इजाफ़ा होगा।